and thank you all for coming. My project is essentially the growing self-catalyzed gallium arsenide nanowire arrays, which is very similar to what Martin Adjison was talking about this morning. But the focus of my project is really on growing ordered arrays using nano-patterned silicon substrates. And so first I'll just kind of reiterate why we're using nanowires. And so nanowires have several properties which make them interesting as potential building blocks for many electronic devices, including PV devices. And much of this has to do with the unique material combinations and structures that you can build into nanowires. And so essentially this freedom that we have is due to the fact of the large aspect ratio of the nanowires and the small diameter of the nanowires. And so this allows the lateral sidewall surface of the nanowire to relax a certain degree of misfit strain. And so with nanowires, we can engineer novel heterostructures, which you usually wouldn't have access to since you'd be restricted to the lattice match material families. And so with nanowires, you can grow, say, GaAs nanowires on silicon, for example. We can also use inexpensive or even flexible substrate materials. And we can grow structures like core shell and axial structures into the nanowires, like shown in these TEM images. And so for electronic devices, this really opens up a lot of opportunities. And so this is a illustration of a solar cell design for a 1.7 EV PIN top junction, which is grown directly on top of a silicon cell. And this entire scheme is really enabled by using 3,5 nanowires, like gallium arsenide phosphide, for example. And the main benefits of this design is that it has a very low material fill factor, so you're using less of the expensive 3,5 material. The radial junction design allows you to efficiently collect the photogenerated carriers. And nanowire arrays themselves also have natural light trapping properties. And so it acts as kind of its own anti-reflection coating. And so this design has maximum theoretical efficiency of up to 33%. And so many of us in the nanowire field are working on PV devices similar to this one. And so my project really has to do with trying to take nanowire PV to the next level. And the reason for that is because an unpatterned nanowire growth often looks like this SEM image here, where you have the nanowires essentially growing at entirely random positions and with a large dispersion in the obtained lengths and diameters. And often you also get this parasitic crystallite growth as well. If you pattern the nanowires, then you can optimize their electrical properties, like Andrew was talking about, by controlling the dimensions of the nanowire. You can also control the spacing between the wires so that you can optimize the light trapping characteristics. And by patterning, you can also simplify the contacting of the device and eliminate this parasitic growth. And that will reduce the possibility of shorts in your device. And so growing patterned arrays of nanowires using the self-catalyzed method is essentially VLS nanowire growth, whereas instead of using gold, a group 3 component of the nanowire material itself forms the catalyst. And so essentially how this is done is that you put down a layer of oxide on your substrate. And so the substrate material here is silicon, 111 wafers with between 10 to 30 nanometers of silicon dioxide grown on them. And then the idea behind the mechanism is that during the early part of the deposition, gallium droplets will form in holes in this oxide layer. And then those droplets will eventually become supersaturated, and then they'll precipitate the solid nanowire material. And so these holes in the oxide layer can either be formed through a natural process, or you can pre-pattern them, which is what I'm doing. And so, like Martin Adjison mentioned this morning, there's a few reasons to use this self-catalyzed mechanism in particular. The first reason is because it is a gold-free growth process, and so you don't have any risk of introducing any gold deep level impurities either in the nanowire or into the substrate. These self-catalyzed nanowires have also been grown with very high material quality, with high phase purity and low defect densities having been achieved. And you also have the ability to consume the catalyst droplet, which will stop the growth of the nanowire and allow you to grow more uniform shells. And this helps in forming the radial PN junctions. And so patterned self-nanowire growth can be done by patterning an array of holes into a thermally grown oxide layer on silicon. And so currently I'm using the electron beam lithography facilities at U of T to do this. And I pattern a hexagonal array of holes like this, shown in this SE image. The typical hole diameters that I use are between 50 to 100 nanometers. And the spacing between the holes, or the pitch of the pattern, is usually between 250 nanometers up to 2 microns. And using EBL, it's relatively straightforward to pattern a single sample with the different combinations of these parameters. And so you can have like a 5x4 array on this sample here with different hole diameters and spacings. And with this, you can then study how these parameters affect the growth of the nanowires. And so next I'll start talking about some of the results that I've had. And so initially we worked on finding growth conditions in our MB system that gave reasonably good nanowire growth. And then we encountered a few issues. And the main issue that we encountered was that the growth results were not entirely consistent. And so this set of images shows a comparison between 3 different samples. The first sample, where the pattern was transferred into the oxide layer using a 20-second dip in buffered HF. The second sample, which was not patterned at all, but where the nanowires just grew naturally and kind of randomly on a thin native oxide surface. And the third sample, which was transferred using a 1-minute carbon tetrafluoride reactive ion etch. And these 2 pattern samples were patterned identically, so they had the same EBL parameters, and they were grown under identical conditions, but they have very different results. And so in the first case, you can actually see, it may be hard to see from your vantage point, but there's actually some unoccupied holes, some empty holes in the pattern. And there's also a large diameter, large dispersion in the lengths and the diameters of the nanowires. So you get these tall and fat nanowires in the array, and you also get these short and skinny nanowires, which is very similar to what you see in unpatterned growth. So you get the tall wires and the short wires. Whereas in this third case, the array obtained had relatively uniform dimensions. And so we used a focused ion beam milling system to take kind of a cross-sectional slice of these samples in order to study the nanowire silicon interface. And what this revealed was that using this 20-second buffered HF etch really badly undercut the holes, and so it gave much larger holes. And it also was very unreliable in that, for whatever reason, there was a very thin layer of oxide left on the bottom of the holes, and so there's like 20 angstroms of oxide here. And what that meant was that the gallium droplet first had to dissolve a hole through that thin oxide before making contact with the silicon. So you can see that in this 10 nanometer area here. Whereas for the reactive ion etching technique, much smaller holes were obtained. So these are only about 50 nanometers, and no residual oxide was left. So these smaller oxide-free holes definitely had improved length and diameter dispersions. And so the length and diameter was very close to some average length and diameter for these samples, which is what you want from patterning nanowires. In addition, we were also able to grow these samples for different times. So by growing for 5 minutes, 10 minutes and then 15 minutes total growth, it became clear that these nanowires also have significant radial growth. And so you can see that here, the nanowires are getting thicker, and you can also see that on this plot here, the measured length versus radius for a growth time of 5, 10, and then 15 minutes. And this actually explained why these badly etched patterns, like this data set here, and unpatterned samples have this roughly linear dispersion of lengths and diameters. And this is because, in this case, the gallium droplet first has to dissolve through that oxide layer. And so that meant that the nanowires can start growing at different times during the deposition. And so the tall nanowires all started growing early in the deposition, so they all have much larger diameters, whereas the short nanowires started growing late, and so they've had less sidewall growth. We were also able to study these nanowire growth in patterns with different inner hole spacings or different pitch. And what we found was that the rate of radial growth depends significantly on the spacing between the nanowires. And so when the nanowires are spaced out further, this radial growth rate increases. So for spacing of, say, 2 microns, like in this image, the radial growth rate is around 0.4 microns an hour. And when you put them 250 nanometers spacings, it drops down to 0.1 microns an hour. And so what this suggests is that the more oxide surface that surrounds the nanowires, the higher the radial growth rate. And this isn't actually very likely due to surface diffusion either, because the diffusion length of these add atoms on this oxide surface is very low at the growth temperature. And so what we believe is actually happening is that the droplet is progressively increasing during the growth. And so this would cause the nanowires to have like an inverse tapering. And so what's driving the radial growth of the nanowire is that there's a secondary flux of add atoms, which is evaporating off of the oxide. And this flux of add atoms will then impinge on the sidewalls of the nanowire, and they'll incorporate on these tapered steps. And so just to kind of wrap up, this radial growth could actually be used as an engineering tool to control the overall diameter of the nanowire just by increasing the growth time. And you could also obtain relatively large diameter nanowires without risking a decrease in the crystalline quality, because the nanowire silicon interface is still confined to the hole diameter. And so in this TEM image, you can see that the hole diameter is around 50 nanometers, whereas the nanowire diameter is around 100 nanometers. And so that maintains that strain relaxation. And so just finally, we've been growing silicon doped nanowires recently, and we're preparing those for ensemble and single nanowire measurements. And I've been working towards improving the yield of the vertically aligned nanowires in the arrays, which I found is mostly a problem of tuning the growth conditions. So I'd like to thank you for your attention.